Hello again from Chicago. Today we're looking at pumps, and particularly domestic booster pumps. This will be part one. We have a lot of information to cover. Some of it will be this week and some of it will be next week. This is High-Rise Plumbing Design online from UCLA Extension University. I am David DeBord, and welcome. Again, we're looking at pump basics, and we're trying to keep the presentations down to a shorter time period, so it's not so hard for you to absorb everything. And like I said, this week and next week is going to be full of information. So we're going to have presentations, some narrated, some not, and some case studies and other things. Please try to look at everything. I know, but please try to do it. And we're going to throw in a few tips along the way. Tip of the week: math. With it, you can do anything. That's important. And we use a lot of it with pumps. So domestic pumping systems include pressure boosters, which it's water supplies, open systems, but it also includes hot water recirculation and sump and sewage pumps. But we're not looking at those right now. We're just looking at pressure boosters at this time. We'll look at a sizing overview, maybe a couple of methods, and then we'll look at some types of systems, some cost analysis, life cycle analysis, hydropneumatic tanks, and some installation requirements. A lot of that will be next week, but some of it is this week. And make sure you look at all the materials online. Of course, with pumps, we're looking at a couple of things. We can boil it down to flow, which is the rate of water delivery in terms of gallons per minute. And we could also look at it as head, which is also pressure. But head is the force that we have to overcome to get the water to its delivery point. This can be represented in feet of head, or it can also be represented or converted to pressure as pounds per square inch. Now these are the imperial terms. You'll notice sometimes we'll go to metric, and we have people from all over the world here, so everyone will get a chance to see something in their native mathematical language, and everyone convert that. A lot of times it's not going to be important whether we're using the same numbering system. It will be terms of relative magnitude, etc. So even if you are not using the same form, like maybe you're using metric and we're using imperial or vice versa, a lot of times, sometimes you're going to have to convert that, but other times it's not going to matter if you convert it or not. You'll still get the same idea. So when we look at a single pump selection, and we're looking at PSI versus feet of head. Head in feet equals PSI times the specific gravity of the fluid times 2.31, where head is the feet of head developed by the pump, PSI is pounds per square inch, and of course specific gravity is the density of the fluid. With water, our density is 1, so we don't really need the specific gravity, but we use this sometimes. Actually, I found this somewhere, and then I made the next slide from this, but it helps to show when we talk about feet of head, where does this come from? It comes from a cubic foot of water, 12 by 12 by 12 inches, and that's how it weighs 2.42 pounds. and this varies with temperature, of course, but we're assuming that our cubic foot was 12 inches by 12 inches by 12 inches, so the base would be 144 square inches. So if we look at 1 square inch of the base, 1 foot high, that would be, and we divided 62.42 pounds divided by 144 square inches, we would get 0.433 pounds per square inch. So head and feet equals PSI times 2.31, or the inverse is PSI times specific gravity equals head and feet times 0.433. So try to remember that. And these are at normal atmospheric temperatures. Centrifugal pumps are devices with the primary purpose to produce pressure, and they do this by accelerating fluid to a high velocity, and that provides them with what we call velocity energy. This is a way to express how the velocity of the objects can affect other objects. You, for example. Have you ever been tackled in a football match? The velocity at which the other player comes at you determines how hard you're hit. The mass of the player is also an important factor. The combination of mass and velocity produces velocity energy, and this is another example is catching a hard baseball pitch. There can be a lot of velocity in a small, fast-moving baseball or a cricket ball. Fluid particles that move at high speed have velocity energy. If you put your hand in front of an open hose, a garden hose, you can feel inside a centrifugal pump. We can see the suction comes in, and there's an impeller eye where the suction comes in, and then there are vanes that on the impeller that spin. Inside the volute is the casing, and then it is thrown out the discharge. Here are some of the parts in more detail. We have what we call a stuffing box, you have some packing, and a shaft sleeve, vane, casing, eye of the impeller, the case wear ring, the impeller, and the discharge nozzle. These things are all important parts of the pump. The fluid in the pump is expelled from the tips of the impeller vanes at some high velocity. Then they slow down as they get closer to the discharge connection, and they lose some of their velocity energy. This decrease in velocity energy increases pressure energy. So we have velocity energy and pressure. Here's a little animation. It probably would be better if it was going a little bit faster, but you can find this at lightmypump.com, and maybe it will look a little bit more demonstrative to you. Unlike friction, which wastes energy, the decrease in velocity energy serves to increase pressure energy. This is the principle of energy conservation in action. The same thing happens to a cyclist. It starts at the top of a hill. Speed gradually increases as he loses elevation. The cyclist's elevation energy was transformed into velocity energy. In the pump's case, the velocity energy is transformed into pressure energy. You could try this experiment. Find a plastic cup or other container that you can poke a small pinhole in the bottom. Fill it with water and attach it to a string and start spinning it. That out where we were going with that already. Here's a demonstration. Well, that might be you. You're looking very sharp there, but it's irrelevant. So here you can see our container has a small hole and we have a string attached to it. You start spinning that. The faster you spin, the container, the more water comes out of the small hole. The water is pressurized inside the cup using centrifugal force in a similar fashion to a centrifugal pump. In the case of a pump, the rotational motion of the impeller projects fluid at high speed into the volume between the casing wall and the impeller tips. This is the volute. Prior to leaving the pump, the fluid slows down to the velocity at the inlet discharge of the discharge pipe, which will be the same velocity throughout the system if the pipe diameter does not change. You might want to think about that for a minute. These changes cause the pressure at the pump outlet to increase when the flow decreases. It sounds backwards, doesn't it? But no, it's not, and we'll show you why. How does the pump adjust to this change in pressure? In other words, if the pressure changes due to outside factors, how does the pump respond to this? Pressure is produced by the rotational speed of the impeller vanes. If the speed is constant, the pump will produce a certain discharge pressure corresponding to the particular conditions of the system, such as the fluid viscosity, the pipe size, the difference in elevation, etc. If changing something in the system causes the flow to decrease, for example, closing a discharge valve, there will be an increase in pressure at the pump discharge because there is no corresponding reduction in the impeller speed. So you slow down you have a decrease to the flow, but the pump is still running at the same speed. So you'll have an increase in pressure at the pump. It has to go somewhere. And it can't get out, so it's sitting there. So how does the flow rate change when the discharge pipe end elevation is changed, or when there is an increase or decrease in? Well, the pump produces excess velocity energy because it operates at constant speed. We're assuming it's a constant speed pump. The excess velocity energy is transformed into pressure energy, and the pressure goes up. That's probably why we have the pump in the first place. All centrifugal pumps have a performance or characteristic curve that looks similar to the one shown in the next figure, and we're assuming that the level in the suction tank remains constant, and if there is a suction tank. And this shows how the discharge pressure varies with the flow rate through the pump. So at 200 GPM, this pump produces 20 psig. So you've got 20 pounds per square inch when it's flowing 200 GPM. As the flow drops, the pressure will reach a maximum of 40 psig. So you see that at 100 GPM, we're flowing 100 GPM at 30 psi, but we're flowing 50. If we slow down the flow to 50 GPM, now we're looking at 40 psi. The pumping basics. Let's take a little bit more of a look at that and the system head curves. Here we see the Darcy-Weisbach equation, or I like to say Darcy-Weisbach. I don't know if I don't think we have any viewers from Germany right now, but please don't be mad for me slaughtering your language. And here you see the energy loss through friction expressed as fluid feet of head, and you see we have a friction factor, and we have to consider the length of the pipe and the diameter of the pipe, the fluid average velocity, and the gravitational constant. Note that this applies to centrifugal pumps. Some applications have different pumps. You could have a positive displacement pump or piston pumps, but that's not what we're looking at now. For domestic water and fire pumps are going to be centrifugal pumps. Those pumps produce constant flow no matter what changes are made to the system. Story for another day. What's on a pump curve? Pump curves are very important, but what should we look for on a pump curve? Well, we should see flow in GPM, head in feet. Normally, you're going to see head in feet. Efficiency curves, impeller trims, horsepower curves, a net positive suction head curve, a pump speed, and a non-overloading value. Might not see every one of these on every pump curve, but these are all things that we need to know. Mostly the first things we're looking at are flow and head, and then of course we want to see the efficiency curves, and we have to know what the horsepowers are, of course, etc. And we always want non-overloading pumps. The impeller trims is where we have the same pump, but you might be able to get it with different size impellers. And what we used to do is trim the impeller to get it to exactly the right size. So you might have a 6-inch available and a 7-inch, but you might need a 6 and 5/8 to get exactly the pump characteristics that you need. But now with VFDs, we don't do that as much. But sometimes if you have a pump that's installed, you might trim the impeller if it's not performing as you want it to. So here is an example of a pump curve from a manufacturer. Over here we see RPMs and a model number. Here if you look at GPM along the bottom, you come up and you go over total head and feet. So in this case, if we are looking for about 950 GPM, we have about 105 feet of head, and you can see our efficiency. We're in the most efficient part of the pump performance. You have about 85%. Here we see our impeller size would be 10.875 based on where we were precisely, but we might go with something different and let the VFD do the work. We have a 30 horsepower brake here, brake horsepower. We see 40 horsepower for non-overloading because we don't want to overload the motor. There's our 85.6 actually percent efficiency. That's the highest. We see our NP, SHR, etc. The pump motor is supposed to transfer its energy through the pump shaft and put that energy into the fluid. When the pump is deadheaded, the energy can't be imparted into the fluid in the form of the change in velocity, and instead it's going to be imparted into the fluid in the form of a change in temperature. So deadhead is no flow, which means we're at the maximum head because the pump is running. If it can't go anywhere, the head is going to go up. And what is going to happen? This is going to get hot. We have to have relief valves because this condition, which we want to avoid, can cause a pump to even explode. So you have to have relief valves just in case. Although do that, it could happen. So what's the minimum flow that you need to circulate to protect the pump from this overheating and self-destruction? Well, let's take an example. We have a minimum flow rule of thumb of 25% of the impeller size's best efficiency point. So in this case, we're looking at 85 GPM, the pink line. We take that up to the red curve here, and we're into 67% here, and that's a 5.75 impeller. So if we take 25% of the flow is 21 GPM. So we would consider that that's the minimum flow that we want for this pump. We don't want to flow less than that because we're going to be in danger of damaging the pump in an unsafe condition. Let's take a look at the sizing of pressure booster systems. We need to have the flow rate, which we get from fixture units and Hunter's curve and other things. And the pressure, we need to know what's the incoming pressure, what do we need at the most remote fixture, and what is the what's it going to take to get there. We need to know the height, the distance, the valves, how much pressure are we going to lose away. Main factors that affect the flow rate of a centrifugal pump are friction, which depends on the length of pipe and the diameter, and the valves, etc. Temperature, TMVs, temperature mixing valves, can have a big pressure drop, pressure reducing valves, etc. Static head, which depends on the difference in elevation, and that's gravity, and fluid viscosity. So we're talking about water, but sometimes it's other fluid that you're pumping. So let's take a look at this one, which happens to come from a manufacturer. This is a quick select pressure booster design worksheet from ITT Bell & Gossett, and it's a convenient one that I just picked. I like to make my own spreadsheets, and I'll show you some examples of that. So what do? We add up the fixtures and we use the information in the codes, the relevant code for the project that affects the codes that are relevant to your project, right? It's going to be different for every project a little bit. So you look at the fixture types, the fixture units each, so you put down the quantity and then you add up the total. This is Hunter's curve, and we have flushed valves and flushed tanks are different until they get up somewhere around 800, and then they follow the same curve. Local codes may be different also. I like to use, a lot of times the codes are less stringent, but I like to use all the data in the ASPE data books, and I like to use Hunter's curve. I like to be a little bit conservative there. The final step is to calculate the required pressure that the booster pump has to develop. So here's a table for pressure boost calculation. We look at the static pressure, the elevation, the friction loss, the required system pressure, what's it take to get there, and this will give us our PSI boost. So now we have the GPM from the previous slide where we converted, we got the fixture units and added the GPMs of cooling towers or whatever and got our GPM load, and now we have our PSI. This is a system sizer. I don't use this, but a lot of people like it. You can use it to look for the flow in GPM and the pipe size. What the material is, it gives you the friction loss per foot, per 100 feet of pipe, and a velocity in feet per second. Here's one that I made. Well, this one says 2008. I actually made this prior to that, but this one is 2008. And you might do it a little bit differently, and I have other examples that I will share with you. But here, if you fill in the blue boxes, it fills in the yellow boxes. It calculates them for you and gives you the GPM. The horsepower has to be calculated separately, and I have that on as well. Any questions so far? How about now? Is it time for a break? I think it might be, because we want to keep this short, and now you have time left to read the materials. Again, we included a lot of materials. Please go through and read all of it, view all of the presentations that we included, and then continue to the quiz. Thank you. Any more questions?